Okay, so this is my report on what would have happened if I had written that book. That was the last line in Simon's talk, right? Where you start from the beginning with propositions as types, because that's where I actually started. So it's not a stretch, because I came to session types late in my life, okay? And I started with understanding them through the lens of propositions as session types. Okay, so this is somewhat impressionistic, I guess. For this kind of audience, this is okay. And I don't have any references because I started and then it was snowballing. I said either I give up or I spend another couple of days. So I gave up, okay. So if you're not sighted, you're not alone. I don't even cite myself, okay. Okay, so what is really not different, right? That's because you want to understand the difference, you also understand the similarities. So in the ordinary logic, we have ordinary types. Going back to work in the 60s, we have the distinction between the data type and the phrase type. And in session types, we have the type of a message and the behavioral type of a process, and those are really the same thing. So, I mean, a function type is a behavioral type because you're not saying how the function is represented. You're saying, if I give it an argument of this type, it gives me a result of that type. So that really doesn't distinguish session types in any interesting way. So normally you would say that intuitionistic propositions are related to simple types since 1969. We know that. But here we know, well, linear propositions are session types. So again, it's not really distinguishing characteristics of session types that you can relate it to logic. And then in ordinary types, we prove preservation and progress. Well, we have the properties like session fidelity and deadlock freedom. So it's also not really distinguishing session types from other things. So where do things become different, okay? So the first most important, well, very big difference is that right from early on, there was a distinction between the global and local types, okay? So coming from the functional world, or even the imperative world, if you will, there is no, as far as I can tell, corresponding a bifurcation of types. So I'm actually not 100% sure that a global type should actually be called a global type, or whether it's something else entirely. I'll come back to that towards the end of my talk. Okay. So I don't like the word binary session types because they aren't binary. Okay. You can have multiple clients to a server. You can multicast a message. So it's not really that every channel has two endpoints, even though it started that way, but it doesn't really extend that way. I really like to think of those in terms of global types and local types. And then another thing makes it that it's right from the beginning substructural, and maybe now we're more used to dealing with that because we have languages like Rust. We do quantum computing, which is by nature substructural. So the point that the type reflects some aspect of the process state, and then the thing that is surprising to most people who come from the other world is that the channel types evolve during communication. So in a functional language or imperative language, if X is a variable of type int, it's always going to be a variable of type int. If you have a function from int to int, it's always going to be a function from int to int. It doesn't change as you compute. But with channel types, they evolve. And that was the hardest thing to wrap my head around when I started on this. So I'm going to just focus on two, partly because I don't really understand one. Okay. And I do want to talk about the end about what we have learned more broadly. So I think that at the beginning of session types, there was a very wide gap between session types and what people were doing in functional languages and imperative languages. I think by now the gap has narrowed because people like me have cannibalized session types and taken some of the idea and applied it to functional languages in other contexts, and that diminishes the difference between the two threads, which doesn't, of course, diminish the impact that the session types had. Okay, so I'm going to use a very simple example, and I'm going to use it in the propositions as session notation. So a store, or as you could think of it as a network also, if you do true sharing, it's an external choice, so the client can do two things. They can either insert an element of type A, which is going to be a channel into the store, or they can delete something from the store, to which the provider, the server responds either, oh, there's nothing in there, and then we'll terminate, or there's something in there, then you get the channel of type A, and it behaves again like a store. So the way we type processes is this way. We have a linear context delta, we have a process P, and we have a channel X that is provided by P, and P is the client to all the channels in delta. So I prefer the intuitionistic approach instead of a classic approach because it is more easily related to functional programming. And if you want to integrate the two, it's nice to have that similarity actually to work from. Okay, so what is the correspondence here? Well, I'm just talking, just to explain these types, probably most of you know this thing, external choice. The provider here receives a choice and then continues at type A or B. Implication means the provider receives a channel of type A and continues as B. If it's an internal choice, the provider has to send either go to the left or to the right and then continue with A or B. A tensor B, the provider has to send a channel A of type A and behave like B. And at 1, the provider sends a unit element and says, now we're closing the channel. Okay. So there's no explicit duality here the way there are in many other session type formulations because we have this distinction between the provider and the client, which is embodied in this typing judgment. Okay. And so this, one of the reasons I like this example because it's very close to what Stephanie and I had showed as the universal session types for asynchronous communication, but also it uses all the connectives pretty much that we have. So, okay. So here's a small program that shows type evolution. I only wanted to show it because, like I said at the beginning, it seemed very strange. But so we have a server which provides a store along channel S. So I like kind of not the PyCalculus syntax anymore, but programming language syntax because you have to write programs. I write these programs all the time. I'm giving a course right now on substructural logics, and I had students implement all kinds of programs. And so they actually have to type them in and run them and try them out, and I have an autograder for all of that. So, so you receive a long S, either an insert or a delete label. Okay. So at this point, the type of the channel S is now something that accepts a channel of type A and behaves like a store. And then you have to receive along S some X, which has type A, and after that, S is back to the type of the store. So the only way that I can write these programs, unless you have a lot of experience, is you have to yourself, when you write it, you have to track the types of the channels. It's very strong type-directed programming, much stronger than in functional programming, right? Because the typer gives you a very strong hint about what you have to do at each step in the program. When you delete, then this is the type of the channel. So that's an internal choice. Now we, as a provider, as a server, you have to send, okay, in this case we send, oh, we have something. At this point, channel S says type A cross store A. Now we have to send an element, say Y, wherever it might come from, and then S cycles back to be of type store of A. Okay, so we have this evolution of types, and like I said, this is a distinguishing characteristic of session types that was very different from what people sort of in other domains looked at in terms of types. Okay, so even today in languages like Go, which were not designed that long ago, channels have a fixed type. Okay, so you can't write this kind of program. What you have to do is you have to take like the union of all the possible things that might be sent across the channel, and that's the type of the channel. So you don't have very much information. On the other hand, there's a Faraday session type library for Rust, which encodes some of this state change, which you don't get in languages like Go. Okay, so here's a sample rule for a typing rule. I'm only showing it because I'll have a little bit of that later. But when you receive a long X, any of these labels from the label set L, which is some kind of finite set, then we have to check all the branches. Okay. And so since we're providing channel X, we check all of them against X. But that means that we have to do the same thing on the left-hand side because the provider and the client have to continue to agree on the channel they communicate on. So here, if the client has an external choice between all these different labels, they can pick a label K, send that, and continue with Q. And now the channel X has evolved to be of type A of K. Okay. Okay, so to prove preservation in progress seems at first impossible because, well, the channels change type. How are they being preserved? But what saves you here is that if you look at the dynamics which we specify, this kind of multi-set rewriting style, so you have a receive along channel C and a send of a label K along that same channel, then we pick out branch piece of K, and here we continuous queue. And the way you prove preservation, well, first of all, the type evolves here from this external choice type to A sub k. And then the important part is that server and client agree on the type change. And then the final thing to observe is that C is a private channel between the two processes. So it's an internal action, so the type change is not externally visible at the external interface of the configuration. And that's how you get preservation. And then progress at deadlock freedom also holds and is, I think, much easier to see and to talk about than in the classical setting, actually, because of the way cut is written, we have a natural partial ordering we could induction over. Okay. So, but you have to ask yourself if we backed ourselves into a corner, because a lot of communication is not synchronous the way it's here. So a lot of computation is not linear, it just reuses data. A lot of communication is not dyadic, so it's a multicast, for example, so it's not just two processes. So fortunately, because it's actually based on very sound principles, we can extend this idea of local session types and continue to generalize it in order to sort of accommodate extension past these limitations. Okay. And I'm going to walk you through these because this is part of where the story between regular types and session types start to come a little bit closer to each other. Okay. So the first thing we have to say for asynchronous communication, that messages are processes. And then if you have two consecutive messages on the same channel that are asynchronously sent, one can overtake the other. So you cannot just have a channel change its type when a message is being sent. So if you want to have type safety, you need a continuation channel. Okay. So what happens here is something like this. So if you have this kind of, now I dualize things to put on the other side, you have an internal choice, so the provider is going to send you a label and you branch on what that is. So then previously we just say, okay, X becomes now A sub L, and we have to check that in each branch. And here you receive not only the label L, but also continuation channel X prime. And then X prime is of type A sub L. Okay. And once you do that, the tricky part is what are the messages? Well, the messages look like this. So you send on the channel X, which is this external choice here, not only the label K, but also a continuation channel X prime. And this has to become, logically speaking, an axiom. It says something like A entails A or B. And so because it can't have a premise, because a message doesn't have, as such, a continuation. It does have a continuation channel, but not a continuation process. So we have to type this thing with these kind of axioms. But we can do that. And then the dynamics is actually simplified because we have a process sends along channel C a label and a continuation channel. This one expects one of these labels and a continuation channel X prime. And then it becomes this process Q now depending on C prime. So we can still track the provenance of a channel, so this is still implementable by using like the ordinary notion of a channel, even though it doesn't look like sort of in this abstract theory anymore. And it turns out that ultimately this notion of provenance of a channel, when you translate to the functional world, is related to some idea of data layout. Okay. Okay, so now what does the program look like now? Well, it looks a little different because it has more syntax. But when you receive along S an insert request, you get a continuation channel. Then you receive along S prime an element of type A and a continuation channel S double prime, which is a store. And then you can recurse with this new S double prime here and become a server again. And similarly here, when you send along S prime a sum, you have to give it a continuation channel, and then you have to use that for further communication. So you have to write more syntax than you normally would, but it's still analogous. Okay. So now the second step would be, now that we have asynchronous communication, multicast makes sense. We can send a message to multiple clients. Okay. So for doing that, we have to distinguish between the linear channels, which have a single client, and shared channels, or nonlinear channels, which possibly have multiple clients. And so in the semantics, the green processes here, they are just as linear as before, and these purple processes are messages that are persistent, and persistent in the sense that multiple receivers can receive that without consuming it from the wire. Okay, and so this raises the issue that you have to garbage collect these things, but that's kind of a separable issue. And so then you can multicast, and here is the rule for doing this. Was a previous rule. So to lend along a shared channel, you become a persistent message along the same channel with the same contents. And a persistent message can be received. Multi-set rewriting, this bang is kind of derived from linear logic. It means that this thing here is persistent. So even though it's received by this process, it can still be received by other processes. So in this framework, it's very easy to model things like multicast. Now I'm going to skip over the next part, because we can also do shared services, but I want to move on to talk about other things. So let me, this is a little bit less surprising. Okay, so then you come to the point where you want to combine the linear and the nonlinear types. Because, well, part of your program, you'd like to have messages being linear, being consumed. You don't want to have to garbage collect your distributed system, which is a very hard problem. But sometimes things are just not linear, and so you'd like to have both. And the way you can do that is you can have two layers, a nonlinear and a linear layer, and you can populate it with the usual constructs from each layer that you like. And then you just need to go back and forth and investigate what are the properties of these shifts. You can figure out what these laws are, but basically they form some kind of adjunction. There's really not a lot of variability. Your hand is kind of forced in this. So the mode signifies whether a channel, for example, if you use this for channel communication, would be dyadic or variadic. So if it's two endpoints or one provider with many clients. So the mode just determines essentially at this point whether you have garbage collection or not. Okay, whether it's linear or nonlinear. This difference is significant, so I don't want to downplay it, but unifying it this way is actually a very nice simplification overall. So when we did the original work on propositions as type, we used bang, and bang is much less pliable. You can do a lot less with that than you can do by using these shifts. Okay, so where are we now? Okay, so taking stock. So we started with synchronous linear session types, and the channel types evolves during communication. So now at this point we have asynchronous session types, where the continuation process is replaced by continuation channel. And so now we have combined linear and nonlinear types. Types no longer evolve because we have the continuation channel, but we can track the provenance, so it's still implementable in a reasonable way. So now, the rest of the talk I want to spend on what's the connection to what you might call ordinary types. Okay. Okay. So in order to give that connection, I need to briefly talk about process composition. So the process composition here is not just has a single channel that's being bound, because in the intuitionistic setting, it's nice to have a single channel that the provider and the client agree on rather than have two. But it's not a big difference. And then the dynamics of this process composition is that if you have a process that has this kind of a spawn operation, then it bifurcates into two processes, one executing the provider P, which provides A, and the second one being the client Q, which uses A, and A has to be a fresh channel for this to work correctly. And from the secant calculus, if you happen to know this kind of thing, this is just a cut. So the shared channels get replicated on both sides, and the linear context of linear channels get split, and then you get a good typing rule for that. Okay. Okay, so at this point, really, session types become almost ordinary. Okay, because we can compile functional expressions with a destination D, which is similar to Milner's thing. It was referenced earlier as well, and with Luis and Bernardo, we also looked at something similar. So if you have a functional expression of type A sub m, where m is the mode, could be linear or shared, then you can compile it in this way. And now this process here has a destination. So expression E just returns a value, but here you can't just do that. You have to communicate along some channel D. So what does it look like? You have this composition of translation that E1 applied to E2 with destination D, well, you have to run a process E1 with destination X1. Then you have to run a process E2 with destination X2. And then you have to send X2 to X1 because X2 is the argument and X1 is the function, right? But that's not quite enough. You also have to send it the continuation channel for the result of that application. So you have to send it to D as well. So you send, when you have a function application, you always give it one more argument than you think you need because you have to give it a destination. And then a functional lambda expression is just compiled like this. We receive along channel D, so it immediately blocks and waits to receive. What do we receive? Well, a value, the argument X, and then a new destination D prime for the result. And then we evaluate the body with this new destination that we've just received. And when we see a variable, we're supposed to compile it just then we forward, which is the identity rule of the sequence calculus, from X to D. Okay, so because we have this composition of translation, at this point it's very easy to interpret what functional programming should mean. We just have to play with the scheduler. Okay, so for example, if we schedule always this until it communicates along X1, we schedule this until it communicates along X2, and then do this, we get kind of a call by value interpretation, and so on. And here's a simple example. Lambda XX applied to D just receives along D the X and a D prime, and then forwards X to D prime. So it's what you would expect the process to do. Okay. So the parallelism is possible, but you can get called by need, for example, in the following way. So you run this first part until it blocks on X1, and that means that it's now of this form and trying to receive a value. You suspend this, you don't actually run it quite yet. And then you pass this channel X2 to X1 with destination D. And when the function actually needs the argument, that will be a point of synchronization where you have to wake up this process and have it compute enough information that you can continue. So at this point, we have kind of combined functional programming, if you will, with a call by need or call by value or futures if you want to run things in parallel with the usual session type interpretation. Okay, so let me circle back now. So what is so special about the session types? So this is one, okay. I graded out because I didn't, like I said, I didn't really understand it yet. And then we have the substructural, which are linear affine types that reflect process state and evolve during communication. But we can put this in a larger context. We can revise and extend it, for example, to accommodate asynchronous communication, which requires continuation channels, which have suitable provenance. And then we have nonlinear types, because once you have asynchronous communication, it's relatively easy to add that. And then we combine them, and we can actually using that. So if you import this ordinary function of programming, what this translation gives you is what's called futures. So this is known since 1985. So you can have a sub-expression that you evaluate in parallel with the body of the function, and you only synchronize when you need that value. And that matches exactly what we're doing here. So I guess you could say that asynchronous session types is just a type system for futures. Okay? But we don't have to stop there. We can be a little bit more expansive. So, and then me and some collaborators have cannibalized the session types for mixed linear nonlinear types, which originally came from this problem. And then you can use it on the functional side to avoid garbage collection or reuse memory aggressively instead of having to deallocate it. And then the continuation channels that arise from the asynchronous communication actually give you a handle on how you might prescribe data layout in a functional language. Okay, so what I've learned here is, well, overall, first, the significance of linear types. Of course, I knew about them before, but I didn't fully appreciate them in the setting. Then the significance of mixing linear and nonlinear types. The elegance of futures, because they have a very clean, simple, elegant type system that's essentially just session types. And then also the connection between channel provenance and data layout. What I still don't know is fundamentally what are global session types. I've learned something here, okay, in the workshop so far. So I think I'm coming slightly closer to understanding that. and how they connect to local session types. And also what will global session types mean beyond just session typing? If you try to import these ideas to functional language, what would it be? Would that be something interesting? I don't know. Okay. So that's my last slide. Maybe this is a good slide to stop on because there's a lot of things I don't know. Okay. Okay.
Remember, you are using this language for education, right?
Yeah.
And this stateful session types, you need to write a lot of continuation. So how students feel? They manage to write program without confusion, or
Well,
they feel it's a bit difficult?
I can only tell you they manage to write programs. I don't know whether they can write them without confusion. Okay. So because so when I taught a course previously and I didn't have an implementation, they had to write the code by hand and hand it in and grade it, and it was a sobering experience. Okay. How do you grade a piece of code that doesn't even compile? Okay, so I decided to write an implementation, and now everybody got it right. Okay, so, but I don't know how often they iterated before they got it right. I don't know, but they were all able to learn that, and they're able to write like visitor pattern type things in object-oriented programming. So they were able to write quite sophisticated linearly typed code in the homework assignments. Okay, so having an implementation makes a huge difference because they get this instant feedback that allows them to see, oh, there, I'm telling them variable X is unused. What happened here? They can analyze it. So for example, I asked them, the very first thing I asked them to write conjunction on Booleans encoded as 1 + 1. And so they say, okay, well, if the first argument is false, I don't need to check the second. And of course, that's not linear, right? They get an error message saying it's not linear because you don't use the second argument. And so then they go and fix it, right? So I spent most of my time actually implementing error messages, okay? Which is probably a common experience for people who try to use these kind of things in education. But I can say, so far it's paid off, okay? So we'll see what happens in the second half of the course. So.
Okay, thank you very much. Very great. Thank you.
Hi, nice talk. I have maybe a comment about your point one about the connection between global types and local types, the one you say you understand less.
Yeah.
I think what that means, what that represents is actually the connection with concurrency theory, and in particular the theory of process calculi, which were introduced with that distinguishing feature of being able to express both specifications written with what Milner called the dynamic operators, like plus and prefixing, which are syntax for LTSs, essentially, and which give you the sort of temporal dimension of a system, and implementations which are written with both these dynamic operators, but also the static operators, which are parallel composition, restriction, rename, or whatever, and which give you additionally also the spatial dimension of a system. So I think that kind of connection between a global sequential specification and sort of distributed implementation was already present from the very beginning in the theory of process calculi, and I think this is something new for maybe compared to classical type theory, and it comes from, for me, it comes from concurrency.
Yeah, thank you. I think that makes sense. It also explains why I don't understand it. But I have learning to do. I'm always willing to and interested in learning more. And so one particularly interesting question, if I solve what the issue is here, if I can really understand the pi calculus, then what does it mean like for an ordinary functional language? Is there any meaning associated with that distinction? Because the closest I could think of is if you have a language with dependent types, you can express the specification and implementation in the same language. You erase all dependencies before you run it. But here, there's so much more going on that it didn't seem to be a good analogy. I think there's a lot more going on here than is going on in the traditional type theories. So yeah, I'm looking forward to understanding this better. And like I said, there were some talks today, and I talked to Jorge as well. I think I've already started making some progress on that.
There are no more questions. Let's say thank you again.